3D printing is an emerging technology with the capability to revolutionize small-scale manufacturing. This is due to 3D printing being a semi-autonomous process, where there is no need for someone to be there while the product is being manufactured. Furthermore, the process is entirely controlled by computer software. This means that each product can be changed using software to be unique, without having to completely change the tools and materials used. The final reason is the low startup costs of 3D printing. With current methods such as injection molding, expensive molds must be produced for each and every design put into production. This makes research and development slow due to the long production time for each prototype. One interesting application of 3D printing is in cycling equipment, specifically cycling shoes. Cycling shoes, unlike running shoes, do not need to be flexible, which means they can be manufactured from solid materials as used in a 3D printer. This presentation seeks to answer the question, to what extent can 3D printing technology be used in the manufacturing of performance road cycling shoes? The potential of 3D printing in performance-oriented shoes has already been proven. Adidas, a major running shoe producer, has introduced a new line of shoes incorporating a 3D printed sole which is custom fitted to the recipient. This shows how 3D printing has the potential to make huge technological advances in shoe production. The specific shoe I am attempting to create is already in production through traditional methods. This type of shoe is characterized by a carbon fiber shell with differing methods of foot entry and cleat design. The current method for producing custom high-performance road cycling shoes is to wrap a plaster cast of a foot in carbon fiber. The disadvantage of this method is the huge labour involved in the carbon fiber wrapping. Adam Hansen, a manufacturer of these shoes, stated that over 42 hours and 8 molds go into making each pair of shoes. The major aim of this project was to determine, using the available evidence, the best solution to a number of problems from the key findings. These problems include how to produce a 3D model, which 3D printing technology to use, which material to use, and the shoe's exterior design. The first key finding was how to produce a 3D model of the foot to then design the custom shoe. The first of 3 possible methods was to use photogrammetry software to make a 3D model of my foot. This is by far the simplest method, as it involves elevating my foot above the ground and taking a series of photos in a circular pattern around the foot. However, it soon became obvious that the model it created was unsuitable for the production of a shoe. This is because the foot changes shape as it is pressed against the ground. Therefore, when I took photos of the foot in the air, it did not accurately depict the shape of the foot in the shoe. The second method I found was to use a professional 3D scanning service. Professional 3D scanners are able to make 3D models of the foot while it is under load, which solves the previous issue. However, professional 3D scanning services are expensive, and so I was unable to use this technology. The third and final method I found was to make a conventional cast of my foot using plaster bandages, create a copy of my foot using this cast and plaster of Paris, then take photos of this model for the photogrammetry software. This method, despite being the most labour intensive, was effective in modelling the contours of the foot under load, and it was within my price range. The second key finding was which 3D printing technology to use for the manufacture of my prototype. The first of 3 options was SLS, Selective Laser Sintering. This method melts powdered material layer upon layer with a laser. The advantages of this method are that the object being printed is fully supported throughout the process, and there are a huge number of materials it can print in. This allows features with no support to be printed with ease. The disadvantage of this method is the huge cost associated with this method on a small scale. Due to my lack of funds, I could not use this method at this time. The second method is SLA, Stereolithography Apparatus, which, like SLS, uses a laser, but instead of a powder, it uses a liquid resin. The advantage of this method is that, like SLS, it can print floating features, but it is available at a far lower price point. However, I was unable to use this technology due to not being readily available yet at a consumer level. The final method is FDM, Fused Deposition Molding, which works in a similar way to an inkjet printer. It excretes molten plastic out of the printer head, creating the part layer by layer. The only advantage of this method is it is available very cheaply. Luckily, my school had one of these printers in the Design and Technology Centre. The disadvantages of this method is a small variety in material choices and the inability to print accurately or floating features. Due to the cost restrictions of my project, I decided to use FDM 3D printing for my final prototype. This turned out horribly, with the shoes falling apart when any pressure was applied. However, this technology allowed me to actually create my design, proving that it was possible to 3D print a cycling shoe. The third key finding is which material to use for the shoe design. Cycling shoe soles are designed to be as stiff as possible to maximise power transfer. However, due to the small range of materials available to me, I decided that the stiffness I needed could be created through an exoskeleton instead of the material used. This exoskeleton would give strength in the vertical plane, which is where cycling shoes need to be the stiffest. Because of this, I can have a flexible shoe casing whilst having a stiff sole. There were 3 different materials I could choose from: PLA, polylactic acid, TPU, thermoplastic polyurethane, and nylon. PLA is the standard material for 3D prototyping due to its ease of printing. However, this material is both brittle and weak compared to the other materials. In the context of my shoe, PLA will create a shoe that cannot flex, which inhibits the foot's entry and will break under a small load. The next material option was TPU, which is an incredibly flexible rubber-like material. The advantage of this material is it will bend, allowing the foot to enter the shoe with ease. This is also the material's negative aspect, as its extreme flexibility means the foot does not get support from the shoe walls, causing the shoe to feel unstable. The final choice is nylon. The advantages of this material are that it is incredibly tough and slightly flexible. These properties are perfect for the shoe application. However, nylon is much harder to print and has problems with warping and creating fine details. For my final prototype, I went with the nylon material due to its flexibility and strength. However, the print quality of my shoe suffered, with the final prototype being warped in certain areas. The final key finding for my question was the shoe design choices. There were numerous design choices I made throughout the project. However, the major ones included creating a stiff sole, entry and exit of the shoe, and the integration of a road cycling cleat. To create a stiff sole, I had 3 options available to me. The first option was to buy a prefabricated carbon fibre sole for a cycling shoe, and then connect this to my 3D printed shell. The advantage of this method is it's easy and effective. The disadvantage of this method is the high cost of a prefabricated sole. The next method is to lay out carbon layers directly onto the base of the shoe casing. The advantages of this method are that it is cheap and highly effective. However, this method is highly labour intensive, which defeats the purpose of using 3D printing instead of traditional methods of shoe production. The final option is to create an exoskeleton around the sole of the shoe using carbon fibre tubes. For this method, I would create slots for the tubes in the 3D printed shoe casing. This method is cheap, easy, and highly effective. The entry and exit mechanism was the next choice for the design choice key finding. There were 2 main options for this. The first was a simple shoelace system. The other option was a more complicated boa system, which is used in many high-end cycling shoes. For my prototype, I chose to use a single slit down the front of the shoe with laces due to simplicity. The final major design choice I made was how to integrate the cycling shoe cleat. Initially, I had to choose between either a male or a female cleat. An example of a female cleat is the Speedplay design. This design is easy to print due to its simplistic shape. However, this design requires high tolerances in the model which were not available to me at the time. The other option is a male cleat, such as the Shimano design. The advantages of this design is its low tolerances and that the design is free, so I do not have to draw it from scratch. The negative of this design is that it has many complex features which proved hard to print. For my final prototype, I plan to use an exoskeleton for stiffness, a shoelace entry system, and a Shimano cleat. However, due to time pressures, I was unable to complete all of these. I did not attach the exoskeleton, and instead of a shoelace system, I turned the model into a slipper shape. This slipper design meant that I could get my foot in and out without applying force to the shell. The Shimano cleat, however, worked perfectly, and I was able to clip into my bike's pedals. The final prototype that I created is a reflection of the choices that I made throughout the design process. Specifically, the sacrifices in quality and function that I had to make were as a result of the cost limitations. For this reason, the prototype simply shows what is possible in the future with more resources. In the future, the best way to produce a model will be to use a laser scanning service. This method is highly accurate, quick, and will drastically reduce in price on the large scale. SLA printing will be the best way of printing the future version for this shoe. This is because of its ability to produce custom items cheaply on a large scale. This has been proven by Adidas with their 3D printed shoe line. Nylon, the material used in this prototype, will still be the best material to produce the shoe with. This is because of its flexibility and durability. Furthermore, with SLA technology, the poor print quality will be nullified. The future potential for design features of the shoe is limitless, with multiple designs having their own merits for differing applications. For example, the inclusion of a boa closure will increase comfort, but it will also increase the weight. On the other hand, a lace system is lightweight but does not provide the same level of comfort. This is why the future design choices will depend on each consumer's specific application. With an increase in production, the exoskeleton used in my design may become obsolete. This is because carbon soles, like those used in current shoes, could be produced en masse, reducing costs. This would mean that a 3D printed shell could be glued onto the sole for maximum benefit. The future for the software design of the 3D model is straightforward. The methods I used for my prototype work smoothly, easily, and can be scaled up to the large-scale manufacturing in the future. I used free software to turn the foot scan into a 3D print ready format. This was the most successful part of my project. In conclusion, to answer the question, to what extent can 3D printing technology be used in the manufacturing of performance road cycling shoes? My prototype could not be used as a performance road shoe. However, as I have previously stated, there is great potential in this concept for future development.